All right, welcome there, class. We're here to look at example 5. So let's take a look at what's going on here. Basically, we have a block. It's resting on the floor, and we're given two coefficients of friction, one for static friction and one for kinetic friction. So this would be our static friction coefficient, and this is the kinetic friction. So one thing I want to be very clear on, notice there's no units in here, okay? And again, something that I see a lot students like to do, or I guess inadvertently do, is they assume these things here are equal to the force of friction. Okay, this is definitely a red flag. Forces are measured in newtons, and these are coefficients. Okay, so if we remember our equation for friction, equals mu times the normal force. Okay, we're talking about this thing right here. So that's the first thing I want to point out. Commonly confused and used as the force of friction as opposed to what it truly is, and that's the coefficient of friction. So what we're asked to do here is, what is the minimum force needed to start the box sliding? So basically what that's telling me is that if it's going to be start sliding, okay, that tells me that my initial velocity must be 0. Okay, so it's originally starting at 0 meters per second. Whoops, that's not what I meant to do. Let me grab up here and bring this down. Okay, so that's the thing I want to mention there, and this is now out of order here a little bit. There we go. Then the same force, so we're going to continue with that amount of force. It's going to continue to push after it starts sliding. So as soon as I'm starting to slide, what I'm thinking here is this is what we call kinetic friction, or sometimes we call this sliding friction. And again, because we're up in here, because it's going to start sliding, what I'm thinking here is static friction. Okay, so we're dealing with two different types of friction in parts A and parts B. So when I see this number here, this is the value that I'm going to use in part A, and this value right here is what I'm going to use in part B. Okay, so just kind of conceptually what's going on there is that. Then in part C, this is when a block reaches a speed of 10 meters per second, we're going to stop pushing on it. Okay, the force ceases. In other words, it stops. Again, that doesn't mean that the object stops. It simply means the force stops. And of course, due to inertia, it's going to actually continue. And so it actually says how far. So what we're looking for here is until it stops. So these first two parts of this problem, I'm really thinking dynamics. Okay, dynamics is, again, I'm thinking Newton's second law. And then in part C, this is where I'm thinking kinematics. This sounds a lot like a kinematics type problem. So I'm thinking, velocity originals, velocity finals, times, displacements, things like that as we do that, and of course acceleration as well. So let's go ahead and get a picture drawn on this thing and see what we think about it. Okay, so here we are with our free body diagram, and basically we should have four forces acting on our object. We have, of course, gravity that acts on the object. That's a downwards force, and it's on the block by the earth. Those are the two objects that are involved with that force. We also have the floor that is pushing upwards to keep this block from, of course, falling downwards. And it has to, that's what we call the normal force, and it's on the block because of the floor. We are also told there's a force pushing it. We'll call that an applied force that's on the block, and we're not told what it is, so I just said it's a hand. It's got to be some other object, so we don't really know, but I just made that up for now. And then there's friction that has to oppose that. That's going to be on the block because of the floor. Again, there's contact with the floor, so it's going to make that. Now, there's two different parts here. Part A, where this thing is staying stationary. It's not accelerating, it's staying stationary the entire time, so therefore its acceleration is 0. Part B, we're going to maintain the same applied force. The force of friction actually reduces once this thing starts to move. And I'm going to remind us of something we learned about friction, and that is the amount of static friction. The amount of static friction can vary depending on how much applied force it is. So in this region, the amount of friction required to hold it in place is going to vary when it's not moving, when it's static. As soon as we reach into the kinetic region, in other words, it breaks free, it actually generally, for a lot of things, will actually be less. There's less kinetic friction. And so therefore, it maintains a relatively constant value for the sliding friction, the kinetic friction, for any applied force. So basically what that means is if this force is maintaining the same constant, this thing reduces once we get into part B, where it's starting to slide. This thing will accelerate. It's going to accelerate to the right in our case. Okay, so what my strategy is here in part A is basically I need to write a net force equation. Again, the way I'm going to do that is I'm going to go to my free body diagram, and in this case, because we're looking for something that is a force in the x direction, I'm going to look at the x direction, and that's the only forces that I'm going to pay attention to. So as I go up here to my picture, I'll notice that I do have one force that pushes to the right. That's going to be a positive force. And I have this force here that's going back to the left. That would be a negative force. So if I go down here and I substitute these two forces in, basically I am taking the applied force plus the force of friction. And that's equal to the mass times the acceleration. Now, just a reminder that in part A, the acceleration actually is 0. Because again, we're reaching that point just before it starts to move. So we're saying it's just ready to break free. So we're still having an acceleration of 0. So basically what we do here, if we solve for the applied force is going to be equal to the negative force of friction. All right, so what this means is we're going to actually have to, because we don't know either of these things, we're going to actually have to do a second part. Okay, so basically what I'm going to need to do here is I am going to need to find the force of friction, because we're going to actually substitute that in here. So we got to a point here, we kind of got stuck, so I'm going to need to go out and find the force of friction. And the force of friction, I realize here what I've done, just to make sure that you understand. Basically, I've made a substitution. This is the substitution I've made right here. And I've basically substituted that in. So basically, the applied force will equal this friction here. Now, the problem is I don't know what the normal force is either. So I'm going to need to look in the y direction to find that. So my normal force is going to be found by the net force equation in the y direction. I have two forces in the y direction. I have the normal force that's up, and I have the gravity force that is down. And I guess I should define some positive direction here. That would probably be helpful. Typically, we'll say up is my positive y direction. That may come in handy later. But basically, in this case, then since there's no acceleration in the y direction, again, it's not accelerating off the table or the floor or down into the floor, so its acceleration is 0. So basically, the force of gravity will equal the negative or the opposite of the vector, the normal force. All right, so since we are going to need to calculate the force of gravity, that's calculated by taking mass times the gravitational force per unit mass. And of course, that is, in our case, the negative, because up is positive, so this would be a negative 9.8 newtons per kilogram for the mass, or sorry, force per unit mass. And basically then I'm going to substitute, my last step here will be to substitute the normal force that I've just found over here in to what I found in number 2, which is up here. So what I'm going to do here is there's the force applied. That's being brought right down here. Right here is the mu. And then the normal force is what I found right over here. So this is going to be the mg right there. So let me go ahead and substitute in some values and let's see what we get. So the vector force applied equals the negative. And again, in our part 1, it's 0.7. The mass, I forget what that was. Let's go up here and look. I wrote it down. Let's undo that. Let's see, it was 50 kilograms. So 50 kilograms goes in here. And then we're going to multiply that by the negative 9.8. All right. So after plugging this into my calculator and doing the calculation, I actually end up with a positive 343 newtons as the response for part A. Now here's what I want you to think about. Part B of this problem is very similar in a nature. We still have these same 4 forces that are acting on it. We have this force of friction will actually reduce because we're entering into the kinetic region, and you'll be using a different value here. And the other issue is that the acceleration is not actually going to be 0 this time. In fact, that's actually what we're going to actually try to find. And we're going to do that, part B, in another video.